Hi, the next topic is matrix representation. So basically in this course that we express about regression as matrices. So that's why this course requires the linear algebra as prerequisite. Okay, so the matrix representation. So it's convenient to deal with linear regression with matrix in two ways. The one is the statistical theory becomes simple, and the second, the computation gets much faster. Okay, so we have defined the yi is equal to a times. Okay, so yi is equal to a plus b xi, b times xi plus epsilon I. So we would like to put this, okay, so notation, this equation for I is equal to 1 to n in one equation. So for that purpose, we define the y as the vector of y sub i's, so y1 to yn, so this is n by 1 vector. Then we define x. X is sometimes called model matrix or design matrix. So this is, in this case, the n by 2. Then we prepare the vector beta. So this is a vector of a and b, so 2 by 1. Then epsilon. Epsilon is epsilon 1 to epsilon n, so this is again n by 1. Then we can express this original equations, n equations, into just one equation, y is equal to x beta plus epsilon. So this is because, for example, the y1 is equal to 1 plus a, 1 times a plus x1 times b plus epsilon. So that is exactly this equation. Yeah, then beta hat. So our objective was to estimate a hat and b hat. So we express this as beta hat. Then beta hat is given by x prime x inverse x prime y. So it's much simpler. So actually just one equation gives both a hat and b hat. And also the form is much simpler than what we have seen in the previous video. So the x transposed, x prime means x transposed. So x transpose is actually 2 by n, because x is n by 2, so 2 by n and n by 2. So in x is 2 by 2. So if we take inverse, still 2 by 2. And x transpose is 2 by n, and y is n by 1. So we can take the product, that is 2 by 1. So 2 by 2 matrix times 2 by 1 matrix is 2 by 1 matrix. So actually just a pair of two numbers. So then the first component is a hat and the second component is b hat. And why this holds? And actually the proof is also much simpler than not using the matrix form. So remember that the linear regression minimized the summation of epsilon I square. But epsilon I is actually, okay, so okay, we define epsilon as a vector epsilon 1 to epsilon n transposed. So this is actually the epsilon transposed epsilon, right? So that is actually epsilon is equal to y minus x beta. So our form is y is equal to x beta plus epsilon. So epsilon is y minus x beta. So actually this quantity is equal to this quantity, okay? So with matrix, we don't really need summation symbol, and just y minus x beta transpose times y minus x beta. Then we want to minimize this quantity with respect to beta. Okay, so to minimize the natural, the strategy is take derivative with respect to beta, because, okay, so conceptually, okay, so beta is one-dimensional. Actually, beta is two-dimensional, but conceptually, okay, so think about just the function, maybe z is equal to L of beta, okay? Then at maximizer, okay, so beta hat is maximizer. At this point, the derivative should be 0. So the taking derivative with respect to beta is a natural idea. And actually, the derivative of this L of beta is pretty simple, because beta is, so this function is quadratic function of beta. So if you differentiate with respect to beta, for example, for the second term, that just becomes negative x. So derivative is just negative x. So it's simple, and actually to differentiate this entire quantum rule. So in general, f times g, we differentiate, then this is f prime g plus f g prime. So actually, in this case, the both terms are the same, so it simplifies even more, and this derivative becomes 2 times x transpose times y minus x beta. Actually, we need negative sign here, but anyway, so we have to equate to 0. So if we solve this with respect to beta hat, then we can just move this term, the x prime times x beta, to the other side. Then we multiply x transpose x inverse from the left-hand side. Then we get beta hat is equal to this. So this way that we can prove that the beta hat is x transpose x inverse times x transpose y. So this is very important formula, so memorize it. Yeah, in our language, of course, that we can calculate using matrix representation. So in the previous video, that we regress y on x, so Lm y on x. But here, we would like to calculate everything from scratch with matrix representation. So y is the vector of y1 to yn. So this is price, this is response variable. And x is vector of 1 and vector of square footage. So remember that this is exactly 1, 1, and the x first observation to x 48th observation, right? So this is x. Then you can say that, okay, so x transpose is t of x in our language. So x transpose x, then inverse is solve, and x transpose y. So you can get this beta hat. So the first element is a hat and the second element is b hat. So this is exactly the same result as the output of Lm function. And lastly, we explain the epsilon I hat. Okay, so remember that the y is equal to a plus the bx plus epsilon. Yep. But a and b are just estimated. Then of course the epsilon is not known, but just we can plug in a hat and b hat. So we should say that this is also epsilon hat. If we plug in through a and b, we can identify epsilon, but we only have a hat and b hat. So epsilon is also just estimated number. So epsilon is calculated by the x beta hat minus yi. Or in general, the epsilon hat. So this is the all epsilon 1 hat to epsilon n hat. So this is given by x beta hat minus y. So these are called residuals. Epsilon I hat is called a residual.